This is part one because we're looking at what is floating point binary and what are the different parts such as mantissa and exponent. Later on, part two, we look at techniques to solve different problems. So the beginning part is just what it's all about. We'll kick off with y. So basically in decimal, if you want to move one place to the right, i.e. unit 1 becomes 10, you have to multiply by 10 because the base is 10. With binary, the base is 2. So 10 in binary is 2 times 1, not 1 times 10. So the notation would be, instead of xx 10 to the power of y, we write them in the form xx2 to the power of y. And that's just showing you notation, the difference between decimal for the same amount as with binary. Some more explanation. If we have the binary number, there it is there, we could represent that as 1001 times 2 to the power of 7. 1, 2, 3, 4, 5, 6, 7. Okay, however, 7 is decimal. We cannot do that in binary. So we should use 7's binary representation, so you can see that the exponent 7 becomes binary 111. Okay, the actual number would be notated like this: 1001 times 2 to the power of 111. Now, what is this all about? It boils down to real numbers, and in real numbers we need to store them in binary, obviously, and when they have a decimal part to them, we need to ensure that there is the greatest accuracy possible. So that is why we end up with what's called the real part, the mantissa, with its exponent part, the mantissa and the exponent. And it all boils down to accuracy and range, and we'll talk about that later. The format for representing this is a mantissa field, 1001, and its exponent field, which is 111. I refer to this as a part or a field, and that as a part or a field. There's the full number. It can be written like this, but you'll notice often it will tell you, the exam question will tell you which part is the mantissa if you like, and which part the exponent. Generally speaking, it's 4 for the mantissa and 3 for the exponent. You say, hang on a minute, that's 7 and this is 8-bit binary. Yes, because this is the most significant bit. This is the leading and this is the trailing. The leading bit is a 0, which is a positive number. So it's actually, that is the mantissa with its sign, and that's the exponent. We'll talk about that in a sec. So the floating point binary is representation. It's a way of notating or representing, and it's an efficient method of representing a real number in binary. It is called floating point because effectively the location of the decimal or binary point moves. Real numbers have issues with accuracy due to the fractional component, i.e. the point, the decimal point, whatever, the number after the decimal point. How can we get that accurate? By representing it in binary accurately. Okay, so let's just have a look at this normal scientific notation. Minus 2.3445 times 10 to the power of 3. Immediately we know that this is a negative number, but we have to move it because of its exponent 3 places, 1,000. 1, 2, 3. So the number becomes minus 2, 3, 4, 4.5. Let me just see if. So let's see, 10 to the power of 3, 1, 2, 3. Yeah, so it'll be minus 2, 3, 4, 4.5. This is known as the exponent. You know that from maths. This is now a new term for some of you, mantissa. The mantissa also holds the sign of the number. There it is. Now in binary, that's represented by a 1 if it's negative and a 0 if it's positive. This number is to be multiplied by 1,000, so we move 3 to the right. There we go. Alright, and that is the answer to that. Now, floating point uses the same idea. In other words, the floating or the moving of the decimal. The binary floating point number is in 2 parts. We've already explained that you get the mantissa and exponent. Do you remember what that is called? That is the leftmost bit or the most significant bit, and it tells us if the number is positive or negative. We know that this is a negative number. I just wanted to show you this very quickly, that was a simple representation in the previous slide of 8-bit. This is 32-bit. Sometimes the exponent they put in the front, and sometimes the mantissa is represented after that. It doesn't matter. I'm showing you this just to show you that if they want to be difficult in the exam, they can show you a long binary, but the great thing is it's the same technique, and you can lose trailing zeros anyway later. We'll talk about that, but just to show you, okay, that basically it's the same. This is the sign. This is a positive number. There's the exponent. They will always break it up for you. And this is the mantissa. Right, in this case, it's 0.15625, this 32-bit notation. And another presentation altogether, we'll talk about why 23 bits are explicitly stored and the 24th bit is hidden. We call that the significand precision. The significand bit, the 24th bit, is hidden. We'll talk about that much later. Do not worry about that now. Right, now back to our 8-bit binary. There it is again. We're just going through it again. That's the sign, that's the mantissa, that's the exponent. The whole thing is mantissa, but the first part of the mantissa is your positive or negative. So your question you will be looking for is represent these decimal numbers using floating point format. There are 3 decimal numbers here. And later on you'll see the technique for how these become 010000001. Well, it's a positive. If you can imagine the sign there it is there. That's a negative. There's the sign. This is a positive. That's the sign bit. And this is 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. This is 1-byte binary. And which part is our exponent part? Well, that's very interesting, and that's the technique we need to talk about. Let's move on. Alright, I was just working that out as a proper decimal instead of fractional. Here's your exam question. So at this point I'm going to stop part 1 and we'll pick up at this point on part 2 later.